Hello, everyone. I'm sorry I couldn't make it in person to give this to you, but I hope that this will provide you a little bit of an overview of some projects that you could do, tell you a little bit about what we've been doing, and then I'm happy to talk with anyone at a later time. So at the very end, I'll give you my contact information and some ideas. So one of the things that I'm going to talk about today is a project that we did in my biochemistry course during the fall 2022 semester. And that's where we conducted research in a upper division biochemistry lab with undergraduate majors at San Francisco State. There were 14 students who were in the class. And then after we conducted this research, we kind of merged students into my research lab. There were 8 students from that class then that joined my group and started to perform independent study research in a course called Chem 699. And the goal was to reproduce and validate some of the experiments that we had done during the CURE course, and then try and see if we could extend this research out to something that I was particularly interested in my research group on acetyltransferases. And so what I'm going to give you slides with lots of information on it just because I won't be able to answer your questions. So if you have questions, you can come back and look at this, or again, contact me later on. But the way that I implemented this in the course is that I designed a CURE module on protein purification. And we used standard protocols that we had implemented before to purify the watermelon glycosylate MDH protein via nickel affinity chromatography. And in my group, we are using FPLCs. But everything that I'm telling you about can be extended into gravity flow sorts of approaches. This clone that we were using, it has a non-cleavable C-terminal polyhistidine tag, so it's a poly 6 at the C-terminus. And everyone in the class performed this experiment in pairs, and then they gained kind of in-depth training on how to use the FPLC to purify a protein. So this is kind of like a introduction into how do you purify a protein, how do you purify it using an FPLC, and use the instrumentation. And then we then transitioned into student-led groups on various research projects that kind of morphed out of protein purification strategies. And there were 4 different groups that we had. They were given different columns. So I gave them basically a list of here's all the columns that we have in the lab. You're able to pick whichever column you want, generate a hypothesis to tell me, hey, what do you think is going to be better? Is nickel affinity going to be better, or is ion exchange, particularly anion exchange, for example, going to be better than nickel affinity? And I think at the very beginning, it was really around, can we even use any of these other kinds of technologies to purify this watermelon protein? And the motivation behind this was mainly, at least on my end, to ensure that students were getting more background than just nickel affinity chromatography, so they could get some practical sorts of hands-on skills, because at least in the Bay Area, that's a very marketable kind of skill to have, to be able to purify proteins. And so I'm really interested in connecting techniques that are needed in industry to potential, training in students, so students will have jobs after they leave. And so what I found kind of interesting is that everybody thought any kind of chromatography besides nickel affinity was going to be better than nickel affinity. So that actually generated a lot of possible conversations around, well, why did they think that? And it showed that they didn't really know exactly what to expect. But once they went through these experiments, they were able to really formulate kinds of strategies as to why they thought one might be better over another. So even if they didn't have a really solid idea of what their hypothesis really was, they were able to understand it better in the end. So the different kinds of columns that we had obviously nickel affinity, but then we had 2 different kinds of ion exchange columns. We had cation exchange, only strong cation exchange columns, and then we had 2 different kinds of anion exchange columns available. One was a strong anion exchange and another is a weak anion exchange. We also had a gel filtration column, so just like a desalting column. And we decided to just kind of add that in just so that we could expand the possible columns that they could choose. And you'll notice that there's one here that was a 5 mil column for the ion exchange chromatography. I'm going to come back to that, but that was basically the only column that I had available for that. So that's why it was a little bit of a different volume. What the typical flow then, like I mentioned before, was that we perform nickel affinity chromatography. This is just an example of one of the chromatograms from the students in the lab. Our protein is eluting here. We definitely are using more imidazole than we need, but I don't know if you can actually see. But it works. We've been able to use this procedure to get nice looking protein. Sorry, the gels are a little bit dark here, but this is the band that corresponds to the watermelon glyoxylate MDH protein. And one thing that I want to just make note of is the pH that we're using across all of these different techniques, because that's going to become important, and I'll explain why in just a second. But here we're using buffer that's at pH 8. And so you see that nickel affinity, which many of you probably have already experienced all of this, nickel affinity is giving you quite pure protein. It's not completely perfect, but it's really great for what we're trying to do. And what we did was, I'm just going to show you the results for all of the different students, the different groups rather, what kinds of data they got. Not because I'm trying to explain, oh, hey, this is the best technology, but to just show you the variety of the results and the ability to kind of use this and leverage this to teach them a little bit deeper about how protein purification works. And so if you compare like this chromatogram for a DEA column, which is a weak anion exchange column, you see that students were very surprised because they didn't get just one brilliant peak coming out for the elution profile. And that allowed them to, then they ran every single fraction on the gel because they wanted to see what happened. And they were able to then go back and say, okay, I think that my protein is here, for example. It's showing for DEAE that the protein's not binding very well under these particular conditions. But you can see that you're getting rid of a lot of impurities throughout some of these other peaks in the chromatogram. One thing that we did notice is we're still getting a lot of protein that is being expressed in the soluble fraction. We weren't really sure if that was going to be the case because the pH that we were actually selecting was quite high. We had no idea if this protein was actually going to work or not using these conditions. But one thing I forgot to mention is that the watermelon protein, its PI is 8.1, and we were playing around with different pHs that we could use, and the buffers that we had and the buffer capacity that each buffer that we had was able to use to do. And so basically what we found is that we've got a little bit of wiggle room here. There's a lot of protein that can be expressed in the soluble fraction, but it's going to depend on whether or not at that pH the protein really wants to bind well to that column. So in this particular case, it didn't really bind super well. So then we switched to a strong anion exchange column, same kinds of conditions. This is just error that they got on the column when they were loading the protein. But that showed them what error can look like if you get it in there when you're using the FPLC. But similarly, they were able to identify a small amount of the protein coming out and eluting quite early in anion exchange. We went ahead and used a desalting column because we were trying to explain how you could go from one type of chromatography to another, but you would need to change the buffer in between. And so some people thought that maybe this column would actually purify their protein, their nickel affinity eluate better than just leaving it as was coming off of nickel. Unfortunately, I don't have a gel to show you because it was less protein. We kind of lost some protein around in that particular experiment, but what you can see is that the protein elutes really well here, and then it does remove some impurities that are bound that are smaller. In some ways, this can also be a little bit of a imidazole. I'm not sure that this is actually impurity because we didn't have a really great gel to show you on that, but in general, they could assess where the protein itself would be compared to smaller salts, which would be coming out then later in the column. And then finally, what we did was we checked a cation exchange column. And this one, note we're changing the pH to the opposite end. I didn't go over like pH and PI. If you want more information about that, I can explain later, but since I'm limited on time, I'm going to just try and proceed here. But what is really cool about this cation exchange, this was completely unexpected. We did not expect that, well, none of us expected that one of these was going to do better than the other. Everybody thought, oh, maybe this one will work or maybe that one will work, but really cation was kind of out of the box. And what the students found is that they could purify it really well. They get a really tiny little peak here, and they ran all the different fractions on the gel, and it looked really great. And so this was really a nice example of how students could compare cation exchange with anion exchange, how they had to change the pH of the buffers, how they could relate that back to nickel affinity, and how is it that the proteins are coming off of the columns. We're using salt in one case, like sodium chloride in one case, and we're using imidazole in another case. And they can start thinking about how the column matrix itself is playing a role in the ability of the proteins to bind in different ways. And so this really started a conversation in the group where pretty much everybody concluded that, okay, we can use nickel affinity to yield really relatively pure protein, but cation exchange, at least in the way that they observed the gel, appeared to be an alternative. And this really was interesting because it also, I don't even really remember exactly how this started, but it led into discussions about social justice and biochemistry and access to different methods and materials across different sorts of institutions, and whether or not ion exchange could be used as a more environmentally friendly sort of method as opposed to nickel affinity, not just in terms of like mining the nickel and that kind of thing, but also waste disposal and just safety differences that you need to take into account. At least in the state of California, you can't just dump all of the buffers down the drain. And so we have like very specific rules that we need to follow when we're trying to dispose of chemicals. And so sometimes that can be prohibitive in terms of cost for different institutions, especially with limited resources. And the students really just latched onto this idea and they got really engaged in it and were really passionate about trying to see if they could test this in the future. And so at the end of the fall semester, those students then decided they wanted to look into this in more detail. And so one of the very first things that they wanted to do was say, okay, we have this preliminary data from the fall semester from the class. Can we actually reproduce the results, or was this just a fluke during the semester? And they also needed to figure out if the column size was going to affect the purity. They hadn't taken very good notes about which column they actually used. And so we ended up designing an experiment for them to test a couple of different column matrices in addition to what we had done before. There were a couple of other questions that I'm not going to really be able to tell you about right now, but just know that we ended up really focusing on the second bullet point about the whole social justice theme of things. And students ended up presenting at our COSY showcase, which is a student research presentation at the end of the spring semester. And actually students won a prize for that one. We also extended this research into my research group where we were testing whether or not the strategy could be applied to other proteins. And we basically found that yes, it can. That's the short version of the story. It's more complicated than that, but it can. And then there's kind of this open-ended question that we still currently have about whether or not the polyhistidine tag itself, because it was a non-cleavable system, is actually affecting the purification. Again, I can talk more about this later on. But the first step was, can we actually reproduce the results from the fall semester? And so what we looked into was, first, we needed to ensure that we had the right matrix. So there's two different kinds of columns that Cytiva sells for cation exchange. One of them is called an SPXL and another is an SPFF. And we weren't sure which one they were using. We knew it was a 5 mil column, but we weren't sure because we put a label on the side of the tube. And then when we pulled the label off, the name of it came off at the same time. So that was kind of a fault, not only for myself, but also for students, that we needed to know what we were dealing with. And so what we did was we designed a test where we tried to purify the protein again on each of these columns. what we found was that the fast flow column was the one that actually worked. And so that reproduced the result that we had from before compared to the XL column. And then when they ran the gel, they were able to show, so in this case, what they did was they ran the gel on the supernatant, any of the flow through, and then the different fractions that they got. And they compared their results from the 1 mil column with the 5 mil column. If you look at down here, this band right here belongs to the watermelon protein. And what they initially thought was, oh no, it didn't reproduce the results at all because we have so much, like a darker band here and we have all these impurities. But that kind of led into a conversation about the possibility of overloading in some cases or underloading in other cases. And so what they did in this gel here is they added a dilution of the protein that came off of the column, and they were able to start seeing that some of these impurities kind of backed off a bit. And then when they compared to the 5 mil column, they basically were showing that it's a concentration effect when you're running it on the SDS page, but it's not a completely pure protein, even if you can load less onto an SDS page gel. So this isn't a perfect scenario, but it gets quite pure protein that you could then use another strategy if you needed it. Depends on what your applications are. And so the next steps then that we, sorry, I already talked about this. We basically had these other things that I'm not able to talk about right now. But I wanted to just mention a few kind of takeaway messages that I have in general after trying to do cures for a little while now. I think one really important thing is to work with what you have. So we really didn't go into this having a perfect plan at the very beginning, and we were limited based off of the kinds of buffers that we had, the different kinds of columns. We did have a lot because I had some extra things from my, like when I first started my lab, I had a bunch of different columns that we could use in the actual lab itself, the teaching lab itself. But I think that it's important to keep in mind because a lot of times you can actually do quite a bit with limited resources. So, we didn't test every possible scenario of different buffers and pHs and those kinds of things, but we found enough of a result that we could then build a project out of it. I think another thing is to really be a co-learner in the course. It seems to help with approachability, at least in my personal experience, that students find that you don't know everything and it's okay that they don't know everything too, and that they have the capacity to learn and practice and be a scientist. That was really transformative with this particular class, to see that we don't know what the answer is going to be, but they were able to push through and really test and figure out what's happening when they're trying to purify a protein. And then another thing is to just really be flexible and willing to change, because sometimes that gives a greater experience for students, a learning opportunity, not only for yourself, but as students as well. And then helps engage them. If you have the ability to have like autonomy, I know that's not always the case across different schools, but really read the class that you happen to have, the students, their interest, and it kind of means that you might be changing things as each semester rolls through, but it gives it a little bit of life then and tailoring to those particular students. And then finally, this one's really hard for me because perfect really is not an option. We could have spent a lot of time in the literature trying to figure out, what's the perfect scenario for us to roll with. But I think in the end, students really learned a lot, and we got unexpected results. I'm not going to read through everything that's on here, but I just want to show you that I have a lot of ideas about where you could go with this if you're interested in this kind of a cure. There's a lot of room for optimization. There's a lot of room for different kinds of testing. And I think there's a lot of lessons that can be learned in this. It doesn't have to be for this watermelon protein. I think you could extend that to any of these proteins that you're working with. But one advantage that I would say, and I guess one key result, is that we can still use the protein that has the tag on it to do other purification methods. Another thing that I think would be really interesting in the future is to try and explore kind of alternative methods for determining PIs of proteins. This is something that we're looking at in my lab right now, just from a 3D, a three-dimensional structural perspective. Many of you might already know the answers to this. I don't. But I know that there are some programs that we could actually use to take into account the 3D structure versus the way that we calculated our PIs, just based off of the linear sequence. There's also some ways that students can learn a little bit more about how proteins are being eluted off of columns, how to optimize a purification procedure by playing around with, ionic strengths and elution gradients. I will say that my hypothesis about whether or not the tag is actually affecting this, because the very initial thought was, well, the protein is binding to the cation exchange column because it's positively charged because of the tag. But the more you start thinking about it, you realize that the tag itself can't actually be protonated if it's going to be binding and coordinated by the nickel. So my thought, which could be completely wrong, is that I don't think the tag is the key player in this. I think it's actually the property of the protein itself. But you guys can go and figure this part out if you're interested at all. So feel free to either talk to me or take something that I'm mentioning and really go with it. Ultimately, I think that in order for this to become accessible to other people and other schools, we need to then translate what we've learned with the FPLC into like a gravity flow sort of method. And I think that it's possible that you could maybe even use some of the initial information that we have for those different kinds of columns and build out what a gravity flow procedure might look like. These are the students and that have done the research at San Francisco State, both in my research lab, but then also in the class. And then if you have any questions or anything that you'd want to discuss later on, feel free to reach out to me. This is my email address. And none of the stuff that I'm showing you has been published. So if you're ever interested in doing something like that, if you want to gather data and work together, I'm perfectly happy to talk about that in the future. So with that, that's all I have. Good luck and have a great day.